Hi, everyone. Today, I would like to introduce our work, Adversarial Dual Distinct Classifiers for Unsupervised Domain Adaptation. My name is Tataji. First of all, let's talk about what is domain adaptation. Today, deep neural networks have achieved promising results on various tasks. However, we also notice that most of those achievements are based on a large number of well-labeled data. But actually, in real life, we cannot always get so many well-annotated training data for our model. So domain adaptation aims to solve this problem. And based on this idea, we proposed our model. Now let's talk about our framework. Our framework includes 3 modules. The first one is the feature generator. The source and target domain data have different distributions. So the feature generator aims to mapping the source and target domain data into a shared domain invariant latent space. Then the feature extracted from the feature generator will be input to 2 different types classifier. The first one is the neural network classifier, which is denoted as CN here. The other one is the prototype classifier, which is CP. To optimize such a framework, we have several losses. The first one is the source supervised classification loss, which aims to preserve the discriminative knowledge of the source domain labeled data. The other one is the adversarial dual classifier. This loss aims to evaluate the difference between the prediction from the neural network classifier and the prototype classifier. The other one is discriminative knowledge cross-domain alignment. This loss aims to compact the same classes, but different domain data closer, and also push those data from 2 domains, but different classes further away. And last one is the entropy minimization, which aims to eliminate the uncertainty of the prediction to the unlabeled target data. And overall, we have our final objective here. And here are some results of our experiments. We apply our model to 2 widely used domain adaptation tasks. First one is the office home. The other one is the Office 31. Now we see that our model achieved the best performance on both benchmarks and beat the state-of-the-art results over 1%. Here in figure 2, by removing one specific loss term in our objective, we explore the contribution of different loss terms to our model. Through the results, we see that each loss term has a very important contribution to our framework. Then, for the target domain data, we don't have any labels. So in the training process, we will have to use the prediction of the classifier as a pseudo label. But we have 2 different classifiers. So here, we accept different classifiers results as the pseudo label and also report different classifiers with accuracy here on Office Home dataset. And we see that from the results, the prototype classifier has a better performance with the prototype prediction as pseudo label compared to the neural network classifier and neural network classifier prediction as a pseudo label situation. And then we notice that for those categories has the balanced distribution, which means the source and target domain has a very similar number of samples. The neural network classifier always have a better performance. But for other classes, when the source and target domain has a very different number of samples available for training, the prototype classifier always have a better performance. Next, to demonstrate the contribution of our different architecture classifiers, we compared our results with MCD and SWD. MCD and SWD also seeks to train a dual classifier framework, but they accept 2 completely same architecture classifiers. And furthermore, we also change our model to 2 same structure neural network classifiers. And from the results, we see that our original model has the best performance on Office 31. And that's all for our work. Thanks for listening.